Welcome to this skill session. A skill session is our custom webinar format for our communities at Gerlent, German Talent, and Glolent, Global Talent. More info on gerlent.com and glolent.com. Enjoy. All right, welcome to this new skill session and to this relatively new format of our community at Gerlent and Glolent. And this time I'm happy to welcome Kaya Kupferschmidt, who's one of our first Gerlent members and who will present the topic PySpark, and in detail he will explain that after my introduction, I think. And yeah, thanks Kaya for giving this skill session, and I'll let you take over from here.
Okay, yeah, thank you for the possibility to give the skill session. I'm happy, although I did not participate in the Hadoop skill session 2 weeks ago, but I'm happy that Eve is here. So this was the idea that the PySpark session could be some sort of continuation on that topic. So what's that all about? Spark is a data processing tool, a distributed data processing tool that is used often nowadays in the Hadoop environment. And before I jump into some really hands-on things, I like to present some general concepts, and I try to explain the problem that Spark actually tries to solve. I think this is always important to understand first the problem domain. Where do things come from? What have been the previous solutions? What were the weak points, in order to understand which problem really are solved and what is this tool meant to be used for. So I try to get to the next page. First, I want to tell at least a couple of slides on distributed computing, specifically for data processing. All this new fancy stuff comes from the advertising companies like Yahoo, Google, Facebook, Amazon, and so on, who had the challenge of processing really huge amounts of data, which could not be processed anymore on a single computer. And therefore, they investigated a lot, how can we split up data processing on a cluster of computers on multiple servers. And when you look at the basic types of transformations that you typically have in data processing, you will find that there are only basically, I would say, 2 or 3 operations which need to be distributed somehow. So the first operation is one record in, one record out. And this is the simple thing to do, and it's somewhat trivial to parallelize. If you have many records, you can transform them individually, each of them being transformed with the same logic, with the same function. And this is also the scope how you can distribute work among multiple computers. Unfortunately, LibreOffice is a little bit slow at updating things. So, okay, first you can also batch multiple documents together, and then you can distribute that on multiple servers. This is the idea. So this is kind of trivial, of course, only from a theoretical point of view. Distributed computing is always really hard and really difficult when you really have to implement all this low-level stuff. But, and this is one of the problems that Spark solves, you don't need to care about that low-level stuff. So this is clear if you simply have a simple transformation where you want convert all letters into uppercase letters of records, then you can do that individually for all records in parallel. This is the simple thing to do. The next more difficult thing that could happen is you do not have a simple transformation anymore where all records are transformed individually or independently, but you have to mix records somehow. This is always the case when you perform an aggregation or a group by and aggregation. For example, you want to calculate the average age group by gender or something like that. then you cannot simply transform each age independently of all the records, but you have to sum them up. You have to mix the records, but you also have to split the records according to different genders. And this is more difficult if you do it in a distributed way, because each computer has some sort of all records, some part of all records, some portion, and each computer only has, no computer has the global information on all people in this example. So they need to communicate somehow to calculate the average age. This is the expensive operation. I do not want to go into much detail. This is a shuffle operation, but this can be applied to many types of questions. And again, when my computer decides to show the next slide, this can also be parallelized with an additional complex step called the shuffle operation, where you have to exchange all the records, that all records essentially with the same gender are on the single machine. Then you can independently again perform the aggregation independently for each computer. So this is a kind of end-to-end transformation. The last transformation that you probably require are I/O operations, reading and writing data. Before that, I was only speaking about processing data, but you can, of course, also need to read data and write data. And if your data on the input side is already distributed on multiple machines, this is also more or less trivially parallelizable to multiple machines. And the same is also true when you when it's good enough that your end result is not stored within a single file, but is stored in multiple files on multiple machines, then the writing can also be more or less trivially parallelized to multiple machines. And okay, these are the basic concepts. So we see that there are certain operations which are easy to parallelize, certain operations which are more difficult to parallelize. And this is basically the idea of Spark, to provide these basic operations and lots of abstraction on top of that. Next, as I said, okay, you need some distributed file system for that, like for example, HDFS, that should have been part of the Hadoop session 2 weeks ago. Next, I want to make a small comparison between Hadoop and Spark. Hadoop was the first platform, I think the first open source platform, which was really meant to process huge amounts of data on multiple machines. And people were at first very happy to have this platform. And nowadays it's still standard, at least part of the Hadoop ecosystem is still standard, but it also came with some problems. So let's first have a quick look. What was really great, it was a powerful tool. It allowed horizontal scaling. You could add more and more machines in order to speed up the processing. Essentially, it was not limited by the amount of memory. You could even use a single computer with maybe 4 gigabytes of RAM and process terabytes of data. Of course, that would have taken a lot of time, but it was possible to do so, and it's still possible to do so. It turned out to be a very stable platform, now also enterprise ready with all the security stuff that big companies like to have, and it's today the de facto standard. But on the other hand, actually where people were not so happy anymore was it has a very high processing latency. When you started a Hadoop job, so it's batch job like in the old mainframe world, then it could even take 2 minutes until the job found out that it has nothing to do. And when it really had some work to do, it took even longer. And the performance was also not convincing. Although Hadoop won some sorting benchmarks, people thought, okay, that's nice, but the machines have more power, or we think the machines have more power than we see that Hadoop can actually activate. One of the biggest, weakest point is a very complex programming model. Even simple things are really difficult to program with a built-in mechanism of Hadoop. And of course, it only allowed batch processing. And nowadays, companies want to have near real-time insights, near real-time processing. And this is completely not possible with the things that Hadoop delivers out of the box. And this is where Spark comes into play. So the first thing is that where Spark shines is Spark is fast to write. The upper slide, you don't need to understand it, but you can count the number of lines. It's 6 lines of code. This is a complete famous word count example where you want to count the frequencies of all the words appearing in a document or in multiple documents. And this is 6 lines of code. And when you perform the same thing in Hadoop, it's at least, I would say, 100 lines of code. You have to implement certain interfaces with methods, and you have to set up a job, and it's really difficult and complicated, and a lot of boilerplate code needs to be written. And of course, that slows down development tremendously if you have a lot of code for even simple things, and complex things are really almost impossible to implement. This is the first thing where Spark really shines. The second thing where Spark really shines is speed. In the old world, in the Hadoop world, everything, every intermediate result has to be written to disk. This was simply because it wasn't very flexible. You always had this map-reduce paradigm where you always had certain set of operations, and they always had to persist everything on disk, and the next step would need to read from disk. And Spark changed that. You can pipeline operations, you can keep records in memory, which is much faster. On the web page of Spark, they claim they have a speed of 100. This is, I would say, really very optimistic, but from my personal experience, a speed up in the range of 3 to 10 is really realistic. Okay, so how does Spark actually work? I think this is also interesting. First, you have to understand that in this Hadoop or in this big data ecosystem, a very important decision was made, or it maybe happened simply, to separate computation from storage. And for example, if I have Spark, I can deploy it on multiple different cluster types. Yarn is a Hadoop cluster type, Kubernetes, Mesos, or a standalone mode. And this only provides the compute capability. Below that, I, of course, need to store the data somewhere. And there are multiple options where to store the data. For example, in the Hadoop file system or in databases, you can also store it in relational databases. You can use S3 as a very simple or as a very cheap storage. And this gives you the agility that you can use different tools to access the data at different locations. And with Spark, you can even mix and match accessing data. I already spent now 15 minutes. I will stop the presentation here more or less and come to some hands-on things. Or are there any questions here?
Yeah, guys, you have to activate your mic to be able to ask. But are there any questions so far?
Okay.
Okay, I guess not.
None so far.
Yeah.
So I prepared a small notebook. So this is a Jupyter notebook. This is a Python notebook where you can interactively run things in the browser, and you can also use it with Spark. I started a small Spark cluster in Amazon. This is for me always the easiest thing to get a reproducible environment and to access the data that is already stored in Spark. And this is actually a notebook that I use as an exercise in my training. And what I have here is I have a data set of weather data, and I want, so these are measurements per hour, and I want to calculate the minimum and maximum temperature per year per country. So this is basically the idea. And I want to show how this can be done with Spark. So first of all my data is stored in S3. This is the super cheap storage in Amazon, so I can easily access the data. And first of all, I need to read in the data. In order to do so, I have to access the Spark context. So this is my entry point to Spark where I can read data. Yeah, essentially where I can read data. And This is done by Spark, .read, and the data format is actually very strange. It's not a CSV file or something like that. It's a very custom format with a, I think, 20-page documentation and 1,000-line parser for that, which I will not be using. I just want to have a look at the data. So I pick a single year. This is where it is stored. I have the storage location. It's in A3. I pick a single year, 2003, and I want to see, okay, how do the records really look like? So I can, first of all, I say I want to limit, like in SQL limit, the whole data to 10 records, to the first 10 records, and I convert it to a pandas data frame. This is just, oh, I should probably start from the very beginning. This is just convenience because the notebook can display these pandas data frames very nicely. So I just want to see the contents of this file. This takes now some a couple of seconds because in the background Spark is really started in the cluster. This always takes a little bit. It's in Java. Java is slow at startup. And this is how the data really looks like. It's not a comma-separated list. It's a ASCII thingy. And at certain locations, specific measurements are stored, and we need to extract them in order to extract the temperature and the weather station ID and so on, just to give you an impression. So it's a little bit of strange data. I do not have a single year. I have many years, and in the next section, I simply read in all the years from 2003 to 2015. And again, I display the first 10 results of that. So this is a little bit Python code. I perform union. I read in every year with the very same mechanism, and then I create a union of all records of all years. This is the idea. Okay, should look like more or less the same, except that I have an additional column called year. Now what I need to do is I have now something called a data frame. And a data frame is something like a table, like in a relational database, and it has a schema, like we know from relational database. In this case, it has two columns. First is the value column, that's simply the whole line of ASCII data is stored in, and the second column is the year. I added this second column during the read operation in the with column, actually. I do not want to go into much detail here. Now I want to present really the more interesting thing. I have this raw weather measurement data, and I want to extract some measurement information, which is simply stored at specific locations in every record. And this can be done with the select command. This is the simple transformation, one record in, one record out, and it works exactly like you know from SQL databases, more or less. Yeah, so I select data from my raw weather, and I already prepared that. It's not completely trivial. So first of all, I select the column called year. This was already part of the input data. And in addition to that, I extract various measurements using a substring operation, which performs exactly the thing that that you would expect. I extract from the column called value a substring from position 6 and length from position 5 of length 6. And this is my first column forming an ID of the weather station. So every weather station, I have many weather stations, every weather station has actually 2 ID columns. And together they form a unique identifier. And the second is at location 11, and it has 5 columns. And like that, I can extract even more values. I prepared that already. I make a copy paste because this is a little bit tedious work. So it's all substring operations to extract something from this ASCII string. And sometimes I convert it also to a number when I know it's a temperature or wind speed. And it's a very simple operation, actually. And now I want to have a look at the result. Again, I take from the result. This creates a new so-called data frame, the select operation, and I want to see the first 10 records, and I convert it to a so-called pandas data frame from Python, which the notebook can nicely display. Now I have something which really looks like an SQL table. As the result of this transformation, I have multiple columns. The first two, USEF and WBAN, are the identifier of the weather station. I have a date and time when was the measurement taken, a report type, a wind direction, a quality flag if the wind direction is really valid. I have wind speed, temperature, and I also have wind speed quality and air temperature quality, which also denotes if the measurement is valid there. The nice thing, this is really real data containing invalid records. So when I want to work with that, I really have also pay attention that I ignore invalid data records. As I said, I want to calculate the minimum maximum temperature per year and country. I already have the year, but I have no information about the country. I only have information about the weather measurement station identifier. But there is an additional file in CSV format, luckily, that provides a mapping of this station identifier to a country and other meta information, which is not so super interesting to us. I can again read this in Spark, read. I can also specify options. For example, I know that the CSV file has a header with column names. So I say, okay, it has a header with column names. And I read as a CSV file at storage location. This is the base path, and it's contained in a subdirectory called ISD history. And again, I want to see the first 10 records. So this is the station meta information, and you see again I have two fields containing each identifier for stations, and I have another column country where I can see which country does the weather station belong to. I also have more meta information on the weather stations, but I'm not interested in all the other columns. I'm only interested in the two ID columns and the country. And now what I need to do is, just as we know from the relational world, I need to join these two tables in order to add the country information to the weather measurements. And then I need to perform an aggregation, a grouped aggregation on year and on country. So this is what I want to do now here. So first of all, I join the weather information that I extracted above against the stations. And I need to specify the matching criteria. So this is the weather column called USAF needs to match the station column called USAF in capital cases. And at the same time, the weather column, the second column containing the station ID called WBAN needs to match in both tables. This gives me a joint table, simply, which now contains all the columns. Maybe I can execute this separately. And I also want to cache that. It's so nice. And I want to look into that again. This really takes now some time. Joining is an expensive operation. Yeah, okay. But so we let it run in the background, and meanwhile I continue. So the next thing that I want to do is I want to calculate the minimum and maximum temperature per country and per year. So in SQL, this would be a group by and aggregation operation. And in Spark, it's really more or less the same, only written in Python code instead of SQL. So the first thing that I perform is a group by operation. And we get the result from our join. So I jump just a little bit up. So we see we have first all the columns which come from the original weather weather stations, and then we have the additional columns which come now from the metadata because of the join. And now I want to perform the group by operation on the result of that, so on the country and on the year. Oh, sorry. The result of this group by operation actually is not a table now. When you think of SQL, when you perform a group by operation in any SQL that actually is a little bit good, you always have to perform an aggregation. I think you do not need to perform an aggregation in MySQL, but this should be considered as a hack. So the next thing that I need to do after I have the grouping information, I need to perform an aggregation, which is now started with an AGG like aggregation, but the syntax is completely the same or very similar to a select operation. So since I have some invalid things here inside to make accommodate for the time, I may copy paste again. So I perform aggregations using min max, and inside each aggregation I also need to throw away invalid values which are marked with this quality flag. But essentially I'm performing a minimum maximum operation of the air temperature and the wind speed, and I also specify the names of the result columns. And yeah, and this can be executed now. And this should give me the result. Maybe this takes now some more time. And meanwhile, it's calculating. So let me briefly give an idea what Spark actually is. So as we see, as you hopefully saw, with Spark, you can perform any operation that you are used in a traditional relational database via SQL. Spark has this Python API, which is, okay, it's not SQL, but it has all the operations. And therefore, you can definitely say that Spark implements a relational algebra. In difference to a traditional database, you can access data from completely different sources. When you have a classical database from Oracle, MySQL, IBM, or whatsoever, the storage of the data and the query execution engine are tightly coupled. And this is really the difference in the Hadoop world. We have storage, and there are different types of them, and we have execution engines. And Spark is one execution engine. It's a very powerful execution engine, and it can read from multiple storage in the same job. But it really implements a relational algebra. You can also use so-called user-defined functions. That is, you can overcome limitations of SQL when you want to do something which is not provided out of the box with functions or things that are available. On top of that, Spark also provides some machine learning libraries, but when you look at them more closely, you find out that they are rather limited. Okay, they are good enough for many things, but when you compare it with first-class machine learning libraries, you find out that there are really some limitation. And this comes back that in order to implement a machine learning algorithm, you need something like an numeric algebra or matrix algebra, and not a relational algebra. But Spark provides a relational algebra. This is nice for data transformations. This is not so helpful for machine learning things. This is why I always say, before you consider using Spark for machine learning, think about the size of the data that you have. Spark really shines when you have terabytes of data. This is a great tool. But when you have less data, maybe only a couple of gigabytes, then Spark is really not the fastest thing that you can do, and not the cheapest thing that you can do. And specifically, if you want to do machine learning, you should definitely look at other solutions. You can get nowadays workstations with 1.5 terabytes of RAM for a reasonable price, and a Spark cluster with a similar capacity will be not cheaper. definitely not cheaper. Yeah, so while we are waiting, are there any questions?
I actually have a question. So is there any plug and play Spark cluster that's kind of open for playing around a little bit and testing with the syntax of PySpark? Is there some kind of tool or platform for that?
I'm not aware of one, but you can also use Spark in a local mode on your laptop, actually. This is also really nice for development. You do not need a cluster for development. When you only have a small data set, that definitely works very, very fine. The main reason why I'm using this AWS cluster here is that this is the easiest thing to access the data that is stored in S3.
Yeah. But is there like a open source kind of S3 cluster with like millions of data sets that you could use?
Yeah, actually, I didn't look much into that, but even Amazon itself provides some data sets, not specifically for Spark, but simply for play around with data sets. And I think that they are not too many, and I forgot the links. I have them somewhere probably, but I think they are really huge, which is an interesting thing, because it's always really hard to find huge data sets for trying out things with Spark.
Yeah, exactly. That would be interesting.
I need to I need to figure out.
Why don't you show the SQL input to the audience?
The SQL
input. You can just write SQL. Why?
Yeah. Okay. Yeah, that is all. Yeah, I still have to wait until things are finished here. Apparently. Yeah, that's actually, I mean, it's actually a 2-node cluster. One is the management node, which does not work anything, and the other one is has a couple of cores, and it's really it's a not so small data set, and hopefully it's still doing something. Yeah, but you can do Hans, right?
Right.
Okay. Yeah, because I don't see you here, but I recognized your voice. So what Hans mentioned, you can even really execute SQL. You can, and this works more or less like this. You can register, create or replace. You can create something like a temporary view from a table. Let's call it.
We cannot see the current line.
Now better?
Yes.
Okay. You can create something like a temporary view, like it's known in SQL. And this was joint weather. And then when you have created this view, you can also really execute SQL. You can then perform the more or less the same query, select when case when temperature qual case when then temperature as min temp year, country. And then you can execute this select statement, and then you can access this table via the name where I registered the name, and can group by year and country. I'm really curious if this still really runs, or if it crashed for some reason.
And the fantastic thing about the Spark SQL logic is that you get a Spark object back, and you can work with it in the computer and just go on with your analyze.
Yeah, you can. Yeah, exactly. You can mix and match more or less this Python syntax and the SQL syntax. So
it's back. The Python cluster goes back.
it finished. It finished. Okay. So this is the result. We have countries and we have years and we have minimum temperature and maximum temperature. So this looks good. There are really cold places in the world. And no wind speed is lower than 0 because negative wind speed is always modeled as a different wind direction. So this looks good. And now I can perform the same thing. And I think that should be much faster now. Okay. Okay, so then.
I think you need an end.
Yeah, that's true. That's true. And yeah, so this is another nice thing to know. Spark does not execute, perform the calculation when I actually specify the transformation. It only executes all the logic when I want to access the result. This allows Spark to build up or to optimize over multiple different transformation steps. So it has more global picture, and this is one of the biggest differences, I think, when you compare that to R data frames or pandas data frames. When you transform something there, it will be transformed immediately, but here it's a lazy transformation. The operation is only recorded in a transformation graph and now executed when I want to access the result, for example, this way. So I have to redo this again, and this is fast. Yeah, it's only the first step only recorded the transformation, and the second step now really performs the transformation, the calculation in the cluster, even if it's only 2-machine cluster here, but it's done in the cluster. And now it's much faster. It's much faster because, and I'm pretty sure about that, because I cached the join data. So the join caching is also lazily. Data is not cached in advance. It is only cached when the record is calculated, and I said that I wanted to cache the join data, so I can now access the join data and only perform the aggregation, and I think that is much, much faster now. Yeah, are there any other questions?
Yeah, thanks for the great insight, Kaya, and also the live demonstration is often tricky, and that was, I think, a great result, and great insight into how Spark and how the syntax really works.
Yeah, this is really scratching only on the surface. Spark is this whole Hadoop thing and ecosystem is really complex to grasp. Yeah, but I want really, my message is, it's a relational execution engine on data that is stored in a distributed storage. You can access different data, you can mix and match, and it's a really great ETL tool. But it's maybe not the best thing for machine learning or advanced stuff.
All right. Any recommendations for machine learning?
I'm not the expert, actually the super expert there, but when I look at the concepts of TensorFlow, I think this seems to be a really great library because it's really very flexible, although it's maybe not the easiest thing.
Yes, I've seen some very cool things done with TensorFlow.
I mean, I think actually it depends on the level, more or less, how you want to enter things. For TensorFlow, I think you have to have some understanding what's going on mathematically, or if you have that understanding, and if you want to have this fine-grained mathematical control over the model, TensorFlow is a really, really great tool. If you are more on an abstract level, maybe other things, simpler things, which abstract the details a little bit more away, are more easily to use. For example, Python scikit-learn, Or maybe Hans, you can also give some recommendations.
I would recommend Pandas data frame and scikit-learn.
Yeah, this is also what I'm seeing, what customers are doing. And also when customers are hitting barriers in terms of performance or size of data, where I have no experience, but what seems to also work pretty well is H2O and sparkling water. H2O is also a machine learning library, and sparkling water is they integrated it somehow with Spark. This is also what I saw that multiple companies are doing. But I think this is really only when you hit a certain limit. So I always recommend, and I'm happy that Hans recommends the same thing. So apparently I'm not completely wrong there. I always recommend start simple, start with scikit-learn. It's very powerful, and only look at other solutions when you hit limitations.
Okay, that makes sense. Any other questions from the audience?
Yeah, I was just wondering, is it, do you have any applications, or, speaking from experience, would you ever choose Scala over Python? Do you know about any sort of applications like that?
So I'm actually, yeah, that's always the interesting and difficult question. I like Scala very much, but the learning curve is not the easiest one. And it also really depends on what you're doing. You can achieve, specifically with the approach, with the data frame that I've been using here in this notebook, you can really achieve a lot with PySpark without paying any performance penalties, because under the hood, everything is executed in the JVM using Scala, except when you begin to use user-defined functions in Python. Then there is conceptually no way around that these functions need to be executed in Python. And this may and probably really will hurt performance. What I always suggest is, if you really make a lot of use of user-defined functions, but you still want the simplicity of Python, then you may consider to follow a hybrid approach, that you have some Scala experts writing the user-defined functions and some Python people, data scientists, using them in PySpark. Because what I'm really seeing is both languages, I think, also have different target audiences. Scala is really for the data engineer, for the people writing ETL pipelines, and Python maybe is more well suited for the data scientists who really wants to perform analytical tasks.
Right, okay, I see. Okay, interesting feedback. Thank you.
Any other questions?
Nope.
Nope.
Okay.
Yeah, then first, I thank you very much for giving me the opportunity of telling something. I hope that it was not, I hope that you learned something, although it's very difficult to put Spark into 20 minutes. Even now it's 40 minutes, 45 minutes. And I hope that you enjoyed it at least a little bit.
Yes, that was great, actually. And we say 20 minutes as a kind of, yeah, optimistic goal that should not necessarily be reached. So I think it was a really good summarized overview, and I personally learned a lot by just watching this.
Great, nice to hear.
And I'm very interested in your RVS cluster.
Okay. Yeah, if you still have some time, I can explain a little bit, and the others can leave who are not interested. Or is this?
Yeah, sure. I mean,
sure.
Sure.
Okay, so yeah, I'm using AWS. AWS has a service called Elastic MapReduce, and I can open actually it here. I first have to move the Zoom window. So there's Elastic MapReduce as a service, and it allows you to create a cluster configured with some Hadoop components. So I go to the extended options. This is more interesting. And you can simply select, okay, which components do I want to have? And so this already gives you some idea about the complexity of the Hadoop ecosystem. And it's not only a Hadoop ecosystem, it also nowadays contains TensorFlow. It contains MXNet, so even deep learning frameworks begin to start to be part of this EMR thing. So this is the approach where you can then simply click, 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 and you get a cluster. You can then select which machines do you want to use. So if I simply next machine, I can say which instance types do I want to have, how much memory do the instance types have. And this is not the approach that I'm using. I'm using EMR, but not via the web interface. The problem or the challenge that I have, that I'm using this EMR for trainings, and I give every participant of a training a separate cluster, and I would click to death if I wanted to deploy it this way, and it will also be very difficult to ensure that everyone really has the same cluster set up. And therefore, I'm using Terraform. Terraform is a program for automating how do you say, not deployments? Do you know Terraform?
What's the German word, maybe?
No, it's a product, Terraform. It's I even don't get the German word because it's a foreign word in German too.
Okay.
To set up clusters in the cloud. And it also supports EMR.
Images, maybe?
No, not images. Let me see. Okay, you can create infrastructure.
You can create infrastructure on scale? Maybe this?
Yeah, no.
Okay.
It's on my tongue, but yeah. Okay, yeah, there you can really specify for example, okay, I want to have an EMR cluster, and it should have the following component, and it should have the following compute resources. But this will give you a cluster that may be accessible from the internet or not, and this is not what you want because, okay, you need some access to that, but you do not want to have that everyone can access that. In order to solve that problem, I actually added a reverse proxy in front of that. So everything is private in a private network, except the reverse proxy. This is forwarded to the outside, and behind the reverse proxy, the different services of the Hadoop cluster are accessible. So I go to the start page. This is the start page of the reverse proxy. And for example, I have this Jupyter notebook, which I have been using. There's also a Zeppelin notebook. I now added HTTPS with self-signed certificates. Therefore, I have to accept these exception rules. And this is the important thing, yeah? So there's a simple user authentication, which ensures that not everyone on the internet can actually access these resources. But it's still very simple. You only need a browser for that, yeah? And this is really important when you give trainings, to keep the technical barrier as low as possible, because people have their company notebooks which are locked down with antivirus, proxy, and everything that you can think of that makes the computer slow and unusable. And you need to cope with that. And that was actually the best solution that I could find, and which I hope now really works out well. Yeah, and you can also actually access or have a look at these Terraform scripts on GitHub, because I'm really always very, very happy to share things. So when you go onto this Terraform EMR training site page on GitHub, you will see the complete, apparently the complete updated scripts and so on to spin up the cluster, and or multiple clusters at once. And this makes it very comfortable. And I even start to use this setup at home. This saves me from buying a super expensive machine, which I would use anyway.
Very nice. Thank you very much.
Yeah, this is really, it's really nice. So I can simply, when I want to start something, I simply have to say Terraform apply, and this will bring up everything. And when I finished, I can simply say Terraform destroy. And when you're using Spot instances, it's also really not expensive. It's of course it depends on the size of the cluster, but it's when you only have a small cluster, a super small cluster to play around, it's maybe €2 per hour or something like that. So that's I think that's a very nice approach. Before that, I was, or initially for trainings, I was using virtual machines, but this turned out to be really difficult because people had notebooks with no memory or no free hard disk, and it didn't work out. And now this solution really, okay, I need to figure out how this exact solution is working, because in my last training, I was still using HTTP in the reverse proxy without security, without SSL. And apparently proxy servers can break WebSockets. And the notebooks, both the Jupyter notebook and the Zeppelin notebook, they heavily rely on WebSockets. And after some research, I found out that apparently using HTTPS instead of HTTP should prevent proxies from breaking WebSockets, because they even don't see it that it's a WebSocket. I'm curious if this really helps. Yeah, and as you just saw, maybe pop up. So today's Spark 2.4 has been released with many new exciting features.
They timed it to this session, I think.
Yeah, exactly. Exactly.
Okay, great. Yeah, thanks for the extra add-on to your session as well.
Yeah, you're welcome. Terraform is also really a great tool. Okay, I don't use it for anything else than for that, but it really helped to automate the whole deployment process of these things. And now, because when you go into a training and you know, okay, I need some resources in the internet for that, and I only want to have them on demand, you want to go into the training with a good feeling that everything works out nicely. And Terraform provides that feeling to me.
Yes.
Yeah, that's a great tip. Actually, I wish I could justify using Terraform, but I don't use AWS enough. So it's just, I do the clicking to death sort of scenario. But
yeah,
I
but
think
it really took me, I think, at the end, multiple days to figure out everything as I'd like to have. But now it's really great. It really pays off in the long run.
yeah, but it does. Yeah.
Okay. Then for everyone, the recording of this video we will share in our Slack channels, so you can rewatch it after we uploaded them. And thanks everyone for joining, and have a good evening. And thanks, Kaya. Thanks again.
Yeah, you're welcome. Thanks for your time.
All right.
Thank you very much.
Bye-bye.
Bye-bye. Have a good evening.
Thank you, Kaya.
Hey guys, thanks.
Bye.